I guess I got into this really fast, so I hit the wrong button here. But anyhow, we're going to talk a little bit. Let me fix my paper here about section 3.2. And 3.2 deals with logarithmic functions. So I don't want to go into a lot of detail about logs, but I want to explain something about them. Okay. Suppose you had a number 3, and you wanted to raise it to some power. You don't know what power it is. Let's take it 10. Let me change it to 10. And I want to raise it to some power. And I want the solution to be 225. Well, we know that's kind of difficult because 10 to the first power is 10, 10 to the second power is 100, but 10 to the third power is going to be 1,000. So what's this going to be? So this is where we use a system that was developed by Joseph Napier, long time ago, 400 years ago maybe, and it's called logarithms. So what we do is we take the log and we drop the 10 down. The 10 becomes our base. This is our base. And we switch the exponent with the answer. So we just switch these two. So this becomes log base 10, we say, of 225 equals x. Well, here we would need a calculator to do it. Grab out the old calculator. Okay, turn it on, clear it out. So what we're going to do is we're going to hit the LOG key, first column. And this automatically is in base 10. LOG is base 10. So 225, finish the parentheses, equals. And this would be, x would be 2.352. We just kind of carried out a little bit. So that's saying that 10 raised to the 2.352 power is equal to 225. Let's see if it is. Let's verify. Now, it won't come out exactly, but it would come out pretty close. 10 raised to the 2.352 power is approximately 224.9, 225. You know, if we carried it out more places, we'd get more accuracy. So it looks like it does verify it. So we can work in base 10. We can also work in base E. Suppose we had e to the x equals 8. And we want to figure out what we were raising e to. So we would say log base e, drop the base drops, and then we switch. 8 equals x. But log base e has its own unique thing. We usually don't write log base e. We usually write natural log 8 equals x. It means the same thing, just over a period. So this is called a natural log. Doesn't seem very natural to you, huh? Base e. And common log is base 10. So we have base 10 and we have base e. Okay, so let's hit ln, and you see ln's down here, 8. Finish your parentheses equals 2.079. 2.079. So what we're saying is that if e was raised to the 2.079 power, we would get 8. How do we verify that? To verify that, we're going to have LN key, but we're going to have to hit second, clear this out, second LN. Second LN will give me E raised to. And we want to raise this to the 2.7, 2.079 approximately power. And we get 7.9996. So that looks like it would be. So that's how we get E. We hit second LN, and then we raise it to whatever power we want and finish off the parentheses. So to find E on your calculator, you have to hit second LN, and that'll give you your E. So now you have a general idea what logs are used for, finding special exponents. So logs have certain principles. Because logs, when we're operating in logs, we're really operating with exponents. And remember, when say you're multiplying two things together, what do we do with exponents? We add the exponents. So when we want to multiply bases, we add the exponents. So when we're working with logarithms, we're converting things to their exponents, and then we add the exponents, and then we convert back by using something called an anti-log, second log. We can convert back to our original problem. So when we write something like this, let's say I wrote this problem right here. Say we're in base 10, log base 10, 6, plus log base 10, 5 equals. What we're doing is right here, this represents an exponent. Log 6, because we're in base 10, is 0.778. See, this is actually what the computer is seeing. It's seeing the exponent. It's seeing 10 to the 0.778 is 6. It's looking at the exponent. Same thing with 5. I'm just going to change this up to a 5. Equals. See, this would be 0.699, let's call it. So what is it going to do? It's going to add those together. 0.778. And we get 1.4769. We just put that. Then we're going to take the anti-log of that. We're going to hit second log. And it should give me, well, hopefully 11. Let's see what happens. Second log. And I got to put that number in, 1.4769, I think it was. No, it didn't come out too great. Okay. Maybe I messed up somewhere. But that's kind of the idea behind it. Kind of did this in a hurry. So if we hit the second log of that, the anti-log, we should come up with the original number. When we write this down, this would be the log. Oh, I see what I did wrong. This is the log of 6 times 5, right? Or the log of 30. So we've changed the times problem to addition, and see the log of 30. This is pretty close to 30. That's where I was kind of goofing up. I was looking at addition here, but this is times. So the log of 30 we could break down into 6 times 5, which is the log of 6 plus the log of 5, the exponents. On a problem like this, you probably wouldn't use logs, except that this calculator converts everything to logs and then converts it back to numbers that you see. You don't even know you're working with logs. When Napier spent most of his lifetime is making log tables, but the log tables are built right into this calculator. BC, before calculators, when I was going to school, we had to use tables, long tables, and then we had to convert them by different methods to get the most accuracy out of them. And now we don't do that so much, but we still have a lot of formulas that involve logarithms because they were written. Logs were especially developed for astronomy because we were dealing with such large numbers, such huge multiplications. We could change a multiplication, you see, like this, to an addition problem. Much easier to add than it is to multiply. So that was the whole idea. So let me go over these theorems a little bit. I don't want to spend a lot of time. M times n, this would be the log of m plus the log of n. But when we write it this way, we've converted it to a logarithm, not a number. If this was a 6 and a 5, it would appear as a 6 and a 5 here, but we actually would be using the exponent. Okay, the same rule works for natural logs. We could just change this to ln, ln, ln. The log, if we want to do division, we can change a division problem to a simple subtraction problem. And this will work in any base, including base E, except we would just call it ln. So we can change that to a subtraction problem, and then we can convert back. This is probably the most powerful thing we use. Log base A of some number raised to a power. If we have something raised to a power, instead of multiplying it like we do, like 4 times 4 is 16, we can convert this over to a simple multiplication. K times the log of m. And this is how your calculator works to find your square roots. It actually converts it over to a multiplication problem. Then it converts it back. And I had an old calculator. When I took the square root of 9, it was one of the first ones that came out. It would give me 2.999 because they didn't have a great rounding function. It was a Casio. And it would give me it wouldn't give you a 3, which we know it should be, because it was converting it to logs. And when it converted back, the conversion wasn't quite there yet. Kind of funny, huh? The log, if the bases are the same, let's say this is a 10 and this is a 10, then the answer is going to be 1. We can just double check it. The log of, which is in base 10 of 10, is 1. See, the log of 1 should be 0. The log of 1 in any base, log 10, I don't need to put in a 10 because we are in base 10, 0. So when you're hitting the log key, it's automatically in base 10. Okay, and I think another theorem that they have is if the base and the number are the same, then you get that exponent. The base and the number are the same. And sometimes we're going to use these rules. We use them especially in integration a little bit more so. This is probably, these are kind of important. This one is useful. And this one is very useful. Suppose I want to take 3 to the x, and I want to get 7. And I'm trying to figure out what x is. So I convert over log base 3, drop the base, switch. The problem is I don't have a base 3 in here. I only have base 10 or base E. So what do? Okay, well, this is where this one comes in. It's the log of the number, and this would be in base 10, divided by the log of the base. But we want to make sure we put those in parentheses, okay? So when we do it, we want to make sure when we put this in, let's say log of 7. We want to make sure we finish that parentheses divided by the log of 3. And this should give me 3 to this 3 to the x. And x should be about 1.77 equals 7. Let's see if it is. Well, we know 3 squared is 9. So 3 raised to the 1.77. Pretty close to 7, huh? So it's pretty cool. So this is an important concept. If we have a base that's different. Now, all these rules also apply to natural logs. So I could also do ln7 divided by ln3. Let's see if it works. ln7 divided by ln3. 1.77. See, it still works. So all these rules are the same for natural logs. Natural log, remember, is base e. Log base e of something. So this would be natural log of x. Okay, so that's a little theorem. We're not going to do all these problems in the book. And if you look at these problems, so one thing that's very important, the natural log of e is 1. How would you do that? Natural log, how do you get an e? You have to hit your second ln. Then you get your e to the 1 power is, and we need to finish that parentheses again, is 1. So the natural log of e is 1. A little hard to find e on the calculator. So to find e, you have to hit second ln, and that will give you e. And if you want to raise it to the 1 power. Okay. And of course, the natural log of 1 in any base is 0. Okay. I've never used a base of 0, so don't ask me about that. Okay. So it seems like this is a kind of a little introduction. You can mess around with some of the examples in the book, but what we want to do is let me do this one problem. I see at the top of page 6, and I'm going to show you a little different way. On this one, they took the natural log of both sides, and then they canceled out the natural log. You could also convert that. You can just drop. This would be ln 0.05. Let's write it this way. ln 0.05 equals, drop the base e, and then switch, negative 0.04t. Man, that might be a little bit harder. You're going to divide that by negative 0.04, and that should give you the answer. Let's see if it actually does. Negative 0.04. It came out pretty close. See 74.89, and they came up with 75. To me, that would be a faster way of doing it, But so you might jot that down. Okay, what we're more concerned with is this little theorem on page 329. This is the one. This is actually a biggie theorem. If y equals ln x, y is a natural log of something, then y prime is 1 over x. It has its own unique derivative. The derivative of the natural log of x is 1 over x. And this is what we're going to work with mostly here. That's the important concept. So let's try some of those. Y equals 3 ln x. Well, remember when we had 3ex? It was just 3x. The first derivative is still going to be 3 times 1 over x, which would be 3 over x. Just like that. ln x, 1 over x. Well, what if we have a little something harder? Y equals x squared ln x plus 5x. Ooh, looks kind of tough. Not really. Y prime is, well, what is this going to be? A, B, and ABBA. A, B prime plus B, A prime plus just the 5x. Nothing fancy about that. So it's A times the derivative of B, 1 over x, plus B. Now B is just going to be ln x times the derivative of A, which is 2x times 2x, plus the derivative of 5x, which is just 5. Okay, so now let's do a little simplifying. Y prime is, these obviously are going to cancel, x plus 2x ln x plus 5. So this we can simplify. This we can rearrange. Usually put the, just like we put e to the x back, we usually put ln x back. Okay, what if we have y equals ln x over x cubed? Okay, looks like a Babs. B a prime minus a b prime over b squared. Y prime equals b, what's that, x cubed, times the derivative of a, which is 1 over x, minus a, which is a natural log of x, times the derivative of b, which is 3x squared, all over b squared, x to the 6. Well, we can see these are going to cancel. We get x squared minus 3x squared ln x over x to the 6. Running out of space here. We see if we can cram it in. So the final derivative, we could factor out an x squared, right? 1 minus 3 ln x over x to the 6. And I ran out of room, but we can cancel these out and just put it over x to the 4th. And that should be our answer. Let's double check it. Yes. Okay. Well, what about chain rule? What about chain rule on this thing? What if we have ln u? Well, that would be 1 over u. Let's put down the derivative of ln u is equal to 1 over u times the derivative of u. Just like we did with e to the x, except it's a power. So let's try a simple one. This is on the top of page 331. Y equals ln 3x. Usually we put it in a parentheses. Y prime is 1 over 3x, not 1 over x, times the derivative of 3x. The derivative of 3x is 3. And then we simplify. Well, in this case, it came out 1 over x again. But that won't always happen. Okay. What if we had something more complicated? Y equals ln x squared minus 5. Y prime is going to be 1 over this whole thing times the derivative of the inside, which would be 2x. Okay, so not much we can do there. Probably just write it as 2x over x squared minus 5. Okay. Ooh, look at this one. Function of x equals ln x. I'm already confused. All right. This would be 1 over the natural log of x, because that's what's in the parentheses. So instead of 1 over x, it's 1 over this thing. Then we got to take the derivative of ln x, which is 1 over x. So we took the natural log of this, which is 1 over the natural log of x, times the derivative of the inside. So it looks like it's going to be 1 over x ln x. You can put a time sign in there if you want, or leave it out. Let's see if that's exactly what they came up with. Finally, the most horrendous problem of all. I don't know. Y is equal to that. Y prime is equal to, you want to always show that you're taking the derivative. Okay, it's 1 over x squared plus 4 over x. I'm going to make this a little longer. I'll show you how to trick on that in a minute. And then we got to do an add up for the inside, huh? So this would be times b times the derivative of a, which is 2x, minus, I put a minus sign on that one problem, I don't know. Minus, it should be minus though, minus b times the derivative of a times a times the derivative of b all over b squared. What a mess. Okay. Well, first of all, a little trick on this is if you have a triple decker like this, we can flip this over, put the x on top. So this is x over x squared plus 4. It's a reciprocal. It's saying 1 over this. 1 over this is the reciprocal. Okay, times 3, let's put a big parentheses here, 3x minus x squared plus 4 over, this should be 3x squared. This should be 2x squared. Why am I coming up with this? 2x squared minus x squared plus 4 over x squared. Oh boy. Let's simplify that. I just do it over here. Times, this would be 2x minus x squared would be x squared plus 4 over x squared. Well, if I did it right, it looks like these two things cancel. This cancels into their x, and it looks like 1 over x. Is that what they came up with? Not even close. Okay, so what did I do wrong? I think we'll go back to the drawing board on this. Oh, look at what they did. Look at what they did. Oh, let's try this one again. It looked like I was doing it right, but not quite. All right, so let's work through this example. They're saying that this is an expansion. And they're saying this is equal to derivative of this is equal to, they're going to expand it out into the natural log of x cubed plus 4 plus the natural log of x. See, they're, no, not plus, but minus the natural log of x. They're changing this to a division problem. They're expanding it out. Okay, then they went ahead and took the derivative of each one of these. So this would be 1 over x cubed plus 4 times the derivative of the inside, which would be 3x squared, minus the derivative of that, which is 1 over x. So now what they did is, this is 3x squared over x cubed plus 4 minus 1 over x. So they tried to get a common denominator. So one trick we can use is the crisscross applesauce. We can multiply x times 3x squared. That would be 3x to the third minus parentheses 1 times this, x cubed plus 4, times x cubed plus 4. Let's distribute that out. 3x cubed minus x cubed minus 4. Watch it distribute a negative sign over, let's go ahead and multiply that out. X to the fourth plus 4x. So y prime equals 2x cubed minus 4 over, and they didn't multiply it out, but I did, x to the fourth plus 4x. So this tricked me up a little bit. So when you had something like this, rather than using an ABBA, they used the expanded log form. Remember, this is going back to this problem right here, where it says if you have a division, you can expand it out. Well, you're probably saying, what about this multiplication? Did we have a multiplication here? No, because this is more of a, just taking a regular log. It wasn't a multiplication. So you have to be kind of cautious about that, huh? It kind of tricked me up a little bit on that problem. Well, what I want you to mainly do, I'm not worried about all these logs on this page, all this stuff. I want you to work on the derivatives. That's what we're working on. And I'm looking at this problem number 65. E to the x ln x. Now, this we would use an ABBA. You notice on this one, this was inside of parentheses. This is outside. This is just e to the x times ln x. This would be an ABBA, a, b prime, a, b, you know. So the derivative is a, b prime plus b, a prime. So y prime is a, e to the x times the derivative of b, 1 over x, plus b, ln x, times the derivative of a, which is e to the x. We can, if we want to, we can factor out an e to the x because it's common to both terms. Might take that out. But don't want to combine that together. This is still 1 over x plus ln x. You can write it either way. You could also write it this way, e to the x over x plus e to the x ln x. Let's see how they wrote the answer in the book. This was 65. I don't have that answer. So I don't know which one they put it in. Let's see if I can find it on this page. I don't see it here. Probably in the back of the book someplace. But that's how I would write it. Anyhow, I'm pretty sure it's correct. You know, if it isn't, I'm in trouble. Okay, so have a little bit of fun with these problems. Try them, practice, you get good at them. And let's end this whole collaboration.